The question is, how small can you go and still find biomagnetism? Richard Frankel collects bacteria from saltwater marshes on the California coast to study their magnetic properties. These bacteria have a problem. They seek food and security in the muck under the pools of water, but they don't have eyes to guide them, and they are so tiny they're unaffected by gravity. The bacteria may be simple single-celled creatures, but they navigate the same way Columbus did.
Looking at the monitor here, we can see bacteria swimming out of the sediment particles and accumulating at the edge of the drop, which is closest to the yellow end of this bar magnet. And now after they've accumulated for a while, I can show you that if I turn the bar magnet around, the bacteria swim away from the drop.
Oxygen is magnetic. Oh, wait a minute. Now, there's oxygen inside us. How come when you walk by a magnet, you don't suddenly go like that? Well, I'm going to show you why. So this is a nice big magnet. Zoom in here, try and get some light on the subject. I think that's relatively clear. We got some shadows here, but maybe if I turn it, there we go. There we go. Okay. Let's try some liquid nitrogen. Now, the reason that I brought liquid nitrogen is obviously there's lots of nitrogen in here now because the air is 80% nitrogen, but you can't see what's going on. So let's condense the nitrogen, and when you condense nitrogen, you get liquid nitrogen. It looks like water, but it's at its boiling point. It's at minus 192 degrees C. Okay, it's cold stuff. You've got to chill down the air to minus 192 before this stuff condenses into a liquid. You don't have to worry about it. You're already breathing. I have to finish that sentence. You're already breathing nitrogen. You will continue to breathe. Now, if we go back and look at the, let's do that, MO diagram of nitrogen, there's nitrogen. No unpaired electrons. So I would predict that this stuff is not paramagnetic. Let's see if it's true. It should not stick to the poles of a magnet. Now simply pour this into the magnet. Nothing happens. It doesn't stick to a magnet. There's no unpaired electrons in it. That cracking sound is the camera, but I'm not going to worry about that. Now we have liquid oxygen. I made this by putting a copper tube inside a flask and filling up the flask with liquid nitrogen and then blowing oxygen through the tube. Oxygen's got a higher boiling point than nitrogen. So you can condense gas phase oxygen into liquid oxygen by pushing it through liquid nitrogen. And I'll just put some in a beaker here so you can see it. It's got a lovely blue color. I'm hoping you can see that color. Okay? It's blue because of the electronic transitions that are going on in here. It's actually a very complex process, but it's one photon exciting two electrons at the same time. And the absorption of radiation is in the red and yellow and green portions of the spectrum, and that leaves the blue for you to see. It's absorbing everything else. So it's liquid oxygen. It's the same stuff you're breathing. I mean, it's not going to hurt me to do this or anything. It's, you know, perfectly normal. But let's pour this through the magnet and see what happens. Isn't that just the coolest demo in the world? I love this demo. It sticks to a magnet. Oxygen is magnetic. It's paramagnetic. It's not your everyday experience. Why would you think it would be? Well, you only see this, of course, because the oxygen is so dense here. It's about 4,000 times as dense as the oxygen in the atmosphere. Let's do that again, as in the atmosphere. So you can only see it when it's a liquid, but it actually sticks in the poles of a magnet. This stuff is so much fun. I actually meant to bring something else because there's lots of things you can do with liquid oxygen. But I forgot to bring something, so unless anybody has some steel wool in their pocket. Some people are actually checking. You carry steel wool often? No? Okay. Okay. But I'll do that when we get to kinetics. There's a good reason for doing that too. So oxygen is paramagnetic. Why is it paramagnetic? Well, let's go and look at our MO diagram for it. There we are there. It's for the simple reason that it's got two unpaired electrons. Now they happen to be, there we go, they happen to be in an antibonding orbital. It doesn't matter. They're still unpaired.
Unlike the pigeons and lobsters, we can actually see the bacteria's internal direction finder. This is a picture from an electron microscope, the organism magnified 100,000 times. The bacterium is a living bar magnet.
Abel did not have a magnifying glass. He couldn't magnify these things thousands of times or billions of times like we have to do in order to see these tiny kingdoms.
Well, what the bacteria did, or what they do, in fact, they're doing it right now out here, is they make these single domain sized particles of magnetite and they line them up in a chain. And this forms a permanent compass needle that is just large enough so that the bacterium is oriented in the Earth's magnetic field as it swims.
But are the bacteria actually heading north? Not really. They're swimming down to where the food is. It works just like the floating needle experiment.
If this is the north-seeking end of my internal compass needle, if my flagellum is back here, if I just start swimming straight ahead, then the Earth's field will align me in a particular direction and I'll swim down to the sediments. When you look at these bacteria, you see this chain of particles looking very much like a backbone running through the cell. And in fact, there's an interesting correspondence between the fact that bacteria can mineralize, can produce an internal mineral. I mean, that's what we do. That's what bones and teeth are.
Now, if you commit fornication, which you do, the whole world is geared to fornication and adultery today. This is what's causing AIDS, it causes syphilis, it causes gonorrhea, all of these things. This last god called AIDS that we have, it's a killer. It's a real killer. The minute it gets into your immune system, it starts killing your immune system. This is what's taking place in the immune system of the Earth.
The new approach is to try and understand the molecular structure of these bacteria and exactly what it is, what enzyme on the bacterium is fighting the antibiotic, is getting around the antibiotic, and literally designing a drug molecule on a computer and trying to then synthesize that molecule so it precisely targets the antibiotic resistance. We have to become cleverer.
Then we simply ask the question, if one species needs 800 and another 500, is there a smaller set of genes that might comprise a minimal operating system? We found that synthesizing accurate DNA in large pieces was extremely difficult. Ham Smith and Clyde Hutchison, my colleagues on this, developed an exciting new method that allowed us to synthesize a 5,000 base pair virus in only a 2-week period. That was 100% accurate in terms of its sequence and its biology. It was a quite exciting experiment when we just took this synthetic piece of DNA, injected it in the bacteria, and all of a sudden that DNA started driving the production of the virus particles that turned around and then killed the bacteria. This was not the first synthetic virus. Poliovirus had been made a year before, but it was only 1/10,000th of active, and it took 3 years to do. This is a cartoon of the structure of Phi-X174. This is a case where the software now builds its own hardware, and that's the notions that we have with biology.